function is a named block of code, a named group of statements. So last time we wrote a function called sing, and every time sing was called, I printed out our lyrics here. I love rock and roll. Python comes with built-in functions, such as print. Now we don't write the print function, Python gives it to us. But it goes out, does all that stuff, comes back, ready to do the next thing. And so here we've used several, well, maybe three different built-in functions. We use the print one, which displays stuff on screen. We use the input, which waits for keyboard input and then returns it to store in a variable. And we use the float function. What's the float function used for? Well, input returns a string of stuff typed from the keyboard. You can't do math with a string of stuff, so it has to be turned into a number. And so float turns it into a number, turns it into a floating point number. In this language, there are two different kinds of numbers.
Should I guess and to see what it is?
Well, you know what they are. There's floating point numbers, like with decimal points, and then there's integers with no decimal points. So if I do type parentheses x, it tells me that x was a float. Sure enough, it had a decimal point. If I do type y, it tells me that it's an integer. And while I'm here, I'm going to mention another built-in function, which gives you information about other built-in functions. If I did this, tell me what dir is.
Directory.
There we go. Right? It lists all the different functions that are part of the dir function. Now that's silly. Normally you wouldn't call it on itself, but like the print function. Give me a directory of the print function. Give me a directory of the float function. Now, so far that's not all absolutely fascinating, right? But we can see that there are some built-in things. Pardon me?
Could you do your own functions with that?
Yeah, you can. You can. And you can embed help strings in your functions so that when you type dir, like we could have made one, that sing function and then type dir sing, and not only would it have listed stuff, but it would have told us, how to use it. And we should get demonstrations of that in the PowerPoint. So that's what a function is. We've got several of them. To get input in one of your programs, you can do it as kind of like a three-step process. Don't necessarily want you to type this in. I'm going to go fast and not bother typing it slowly enough for you to do. Oh, no, it's not Notepad. Let's do Notepad from here. All right. Three ways of getting input, and they're all the same, right? So if I print, what is x, and then I ask for the input, and then I convert it, right? That's one way to do it. Another way is to do it like this. See what I've done here? And like I said, I'm not trying to get y'all to actually do the programming. You don't have to type this in. See what I did here? I combined these two statements into one statement because the input function accepts what is known as an argument. This is an argument. Now, an argument is not a bad thing, like we're getting into a fight. An argument just fills in a parameter in the function to make it behave differently. So here we pass this argument in as argument for the input rather than the print statement. All right, that's two ways. And then the last way. All three of those work. They all work about the same. The only difference here is that since the print statement is separated from the input, the cursor will go to the beginning of the next line before the user types it in. Otherwise, these are all three the same. So what's going on here? Well, it's just like math. You always have to do the things inside the parentheses first, right? If you have x plus parentheses a minus b, that a minus b happens first. Well, the stuff inside the parentheses happens first. So the input statement runs, waits for the user to type something in, and then that is returned and used as an argument for the float function, which converts it to a number that we can do math on. So maybe this is the fastest way of typing it. Sometimes I'll type it that way. Sometimes I may type it that way. It's not to confuse you. It's just that maybe typing it in one line like that is easier than doing it like that. You get to pick. When you write your own program, however you want to do it's fine. So if I mess up the syntax of it, if I make a typo, that's called a syntax error. And then you can have runtime errors, which is when the program crashes because of a mistake. It reaches a condition during runtime from which it cannot recover. However, you can fix those errors, and I'm going to show you how to capture and fix those errors. And I'm absolutely not expecting you to do them at this time, but if you've already taken fundamentals and you've got a fair understanding of using a Python language. What if I did this? X equals input, prints, and you can do this one if you feel like it, you don't gotta. X is equal to input, what is X? And then I try to convert it like that. And if I was going to make this a really good program, I'd put my name up at the top and I'd put the class that I was in, right? And maybe did lecture. I believe this is lecture C. Why do I keep doing that? There we go. My brain is stuck. Thank you, Nathan. All right, so here we go. I got a little bitty program. It's going to crash because I'm going to give it the wrong data. What is X? Here's our error. Could not convert string to float. It crashed. The program stopped running. If I want to make my program bulletproof, there are different things I can do. But one thing I can do is just to catch this mistake. This is what's known as an exception. And we're going to tell it to try the code, but if it makes an exception, handle it. So to make it try the code, what I'm going to do is I'm going to push this line down a few and indent it. The line above it, unindented, is going to be the word try. The line after it, unindented, is going to be except, E-X-C-E-P-T, colon. There we go. And if it gets into this except block, it's because it blew up. So I'm going to print an error message. That was not a number. Substituting 0 or defaulting to 0, right? Something like that. And then so we're going to say X is equal to 0. And then if we print X underneath it, print unindented, parentheses, quote, X equals, end quote, comma X. If I run it and this doesn't fail, then whatever X was from up here is going to work. Right? If I type in 3, it'll print out 3. But if I run it and it catches the error state, then it's going to substitute 0 for X and then keep going on. Now, usually you don't just want to substitute, right? If you ask somebody's age and they type in their age wrong, you're not going to go, oh, well, you're 21, right? Normally, you're going to want to display an error message and make them type it again. You'd use looping for that. But let's not make the example overly complicated. What is X? I'm going to type in good data. It says X is equal to 5.0. It put the cursor there. Not the cursor. It put the decimal point in it because that was the float word, which converted it to a floating point number. If I change that to an int, int parentheses, it's going to turn it into a whole number. Now, normally you don't care. So I always use float unless I really, really need to. If you're expecting them to type in a whole number, for one thing, you better tell them. But another is you need to be aware that if they type in a fractional number but you use int, it crashes. So if I run this and type in 1.1, since I use the int built-in function to convert it to a number, it crashed, right? But we caught the crash. We didn't let the program end, but we did tell them that was not a number. They would get concerned, right? In what universe is 1.1 not a number? Well, we should have told them to enter a whole number, and then we should say, you know, print that was not a whole number, or whatever. So I don't use the int function unless I have to, unless it's really specific that I need to have a whole number, because it'll crash more often, right? At any time they put in a decimal point, it'll crash. So I'm going to flip that back to float. You'll see me use float almost all the time. The only time it has to be a whole number, right? Because you could say you're 35.1 years old. There's nothing wrong with that. But if you're making a menu choice, right? Press 1 to run program, press 2 to repeat, press 3, you know, to exit. and they type in 2.1, right? Well, what was it supposed to do? It should have been a whole number. So in that case, you might want to convert it, something like that. If you're making a choice from a list, maybe it has to be an int. If it had to be an int, you could do one more statement here, though. This looks silly, but you turn it into a float first, then you turn it into an int. For some reason, the int function doesn't mind converting 1.1 to an int. It just hates doing it when it's inside a string first. So if this happened, it would round it down. What is x? If I type in 1.9, rounds it down. Turns it into an int. It doesn't round it up, just turns it into an int, right? Which means it drops everything after the decimal point. What if you did want it to round? Well, you can use the word round there, right? Now to round it. If I type in 1.9, yeah, good. Rounded it up to 2. If I type in 1.1, it'll round it down. And I would assume that it follows the same rules about rounding that we know, right? 1.5 probably ought to round up. That's my guess. Yep, and 1.49 should round down. So, if you want to round your answer, go for that. If you want to just flat out turn it into an integer without any rounding, then do that. But if you're going to do that, I would go ahead and prefix it with that first, so that if they're silly enough to type in a decimal point, it doesn't crash the program. Do you have to do this bit right now? No. At this point, if I type in bad data and the program crashes, that's my fault, not yours, right? You're not on the hook for capturing every single possible error yet, right? We're just starting off. You're not supposed to be able to stand on your head, before we learn how to walk. So don't have to do this, but I wanted you to see that you can capture a runtime error. I'm going to add the word runtime here, and then the conversion to float or int generated an error.
Can you use an if statement to do an error check?
Yes, you could. How could you do that? You could use an if statement to make sure that this was a number. However, the ability to check that the string was a number before you tried to convert it. This is kind of like doing it after the fact, right? You could, use a metal detector to make sure that somebody walking in your house doesn't have a gun. That would be using an if statement. Or, you could throw them out after you see them draw the gun. That's an exception handling. It's usually easier just to do this, because checking for a floating point number to see if it's a valid floating point, a little bit hinky, because it has to check for both all the digits and just make sure that there's only one decimal point. Now you could write a function that did that yourself and then just copy and paste that function anytime you need it. I'm not going to write it right now. So I'm going to put an example, a comment saying what we're doing here. This is an example of using try except to handle a runtime error. And this will handle any runtime error. And when I say handle, what do I mean? It means it catches it and stops the program from crashing, which might be enough, right? But sometimes it's not enough. What if you were trying to write to a file and we got a disful error? Are we just going to print them in a message and keep going? No, we're probably going to quit the program. But at least we might quit it with our own error message rather than let the user see a bunch of red text, pop up on screen and we could quit gracefully, right? We could let them know that something's wrong. We could ask them for a new file name. We could try it again, that kind of stuff. So that's what's going on there. Let's add a comment as to what's going on here. We want an int for some reason, but we'll convert to a float first to make sure they did not enter a decimal point. And again, do you have to do that? Nah. Do I think it's cool if you do? If you need a whole number? Yeah, I think it's cool. But like I said, at this point, I don't care if you're writing what's known as bulletproof programs. What's a bulletproof program? One that doesn't crash even with bad data. As we go along, I'd like for you to get better and better at making your program handle errors. More and more bulletproof. And if you've had fundamentals already, then you're already ready for these concepts, and you can start off doing it if you want. So what I would do to do a better job of this, and I'm not going to give a demonstration of this right now, we will do it, is to turn this code into a function, right? So that I could convert the number myself by calling my own function. And if there was an error, I would loop and ask them for the data again, because I wouldn't want them to be able to quit, right, until I would want to force them to enter good data rather than use a default, right? If you ask for somebody's birth date and they typed in bad data, we're not going to just assume that they were born in the year 2000. Instead, we want to insist that they entered good data. All right, I've done a lot of typing already. I'm going to pause. All right, so while the recorder was paused, we typed additional notes, y'all, those who weren't here. Basically, that an int is a whole number. Just pause the recorder, pause the video, and you can read this. A float is a number with a decimal point. A string is characters, and you define them like this. No decimal point makes it an int. A decimal point makes it a float. Putting quotes around it makes it a string. Doesn't matter that this looks like a whole number or that it looks like a float. It's not a float because of the string, the quotes. So I'm going to make a point about this that I think I made a little bit last time, which is that when you save your program and run it, the first thing it does is it reads all that syntax and it turns it into what's known as bytecode. Now, bytecode we can't read, but that's okay because Python understands it. But it's got to be turned into bytecode first before the Python VM stands for virtual machine. If you've ever downloaded a video game emulator because you really feel like playing Pac-Man, you know what a virtual machine is already. The virtual machine is the stuff that'll run that Pac-Man program, and then you can download a different ROM, right? And then, play Super Mario Brothers or whatever. The virtual machine turns that series of bytes that are saved in that ROM file that you downloaded illegally. I shouldn't be encouraging this behavior, right? Or if you're going to run, a Macintosh program on Windows, or you're going to run an iPhone program on Windows or whatever, you can get emulators that'll do that. I'm calling them emulators because they emulate the behavior of another machine, another computer, right? Feel like running the old Commodore 64 programs, or you feel like running Windows programs on a Mac without installing, Boot Camp or whatever, then you can install an emulator that'll do it. Well, they don't call it the Python emulator because they're not emulating something that existed in the past. But it's called a virtual machine. It does the same thing. And that way they can write Python for the Mac and for Linux and Raspberry Pis and this, that, and the other. This part differs, right? However, that machine needs to turn it into bytecode, but it generates the same result. When the Python compiler goes, it generates the same series of bytes regardless of what platform it's on. Doesn't matter if you're running Python on your microwave. The compiler will turn it into the same bytecode. And then it's only this program that has to be different for each platform. The virtual machine is going to be different, just like if you were going to play Pac-Man, Pac-Man download from on your Mac. The byte file you download that somebody, ripped from the original cartridge or from the original machine would be the same whether you're running it on a Mac or on a PC. That makes Python a platform-independent language, right? You can write a Python program and it'll run on any machine that you've ever installed Python on. Doesn't matter the brand, it doesn't matter the platform, doesn't matter if that kind of computer is completely different, it'll still run. Now this is different. This is using a step called interpreting. That's what makes it run on multiple platforms. Now from personal experience probably that if you tried to play an Xbox program on a PS4, no, that's not going to work. You're going to fork over the money, right, to play it on each platform because those things don't do interpreting. Those programs aren't going to be written in Python. For one reason is that Python is way slower than other languages because it has to have that interpreting action. And it's not a knock against Python. It's just something you have to consider. Instead, you'd write one of those programs like in C++ or some other language that is compiled, translated not into bytecode, but into an exe file, an executable file, a .exe file, or a .app file on a Mac, or whatever they call it on Linux, you know, stuff like that. Because if I want you to be able to run my Python program, I have to give you the source code, right? I'd copy it, paste it in an email, or save it as an attachment, upload it. You have to have the source code to run Python. Now, if you're going to play, you know, Python, or Rock Band, or Fallout or something like that on your PlayStation, you don't get the source code, right? Because if you got the source code, you could turn around and sell it to somebody else, and they don't want that. So instead, it gets compiled into what's known as an executable. That way the user doesn't see the source code. And the advantage of it being turned into an executable, if I crossed off bytecode and turned that into executable, is that it runs much, much more quickly because all the hard work has already been done. The compiler has already been done. So that's C++. C++ does that, and some other languages. Other languages like Python and Java and JavaScript do this step. Something turns it into bytecode, and then something else actually runs it, a virtual machine. And that virtual machine is called different things for different languages just because the inventors of them felt like calling them different languages, different things. So instead of calling it a virtual machine, some languages and programmers call it a runtime engine. Same idea, right? The runtime engine converts it from that bytecode into the specific machine language instructions that'll drive your chip in order to do all the good stuff. And so you know what syntax is now. The syntax is just the rules for forming the correct expressions. So we have several different things going on in conjunction with each other. Syntax equals the rules of the language, right? And then the logic is the order of statements, right? I can't use this to calculate anything until I have that data already. So I better put my input statement above the place where I use it. And I better convert it above where I use it. So usually I have a three-step process. I get my input, I convert it, I process it, and I display the results. Now in a fast-moving video game, this is going to be a loop, right? It's going to do over and over and over. The input's going to be waiting for keystrokes, right, to control your character or the input controller or whatever. So it's getting constant input, it's converting it, it's updating its mental model of what's going on, and then it's displaying the results. Now, of course, this is considerably more complicated for a complicated game. We're going to be writing easy programs where, you get your input and you calculate it, what are the number of pounds, whatever, what's the pressure of air, of oxygen, so blah, blah, for this particular volume and this particular density. This is usually just going to be a couple of steps, and then we display the results without a loop, but we'll learn about looping. And by the way, if you feel like writing a Python game, just for funsies, download Pygame. And it comes with examples. So you feel like making a kind of a Super Mario platforming game, I'm sure that there's an example for Pygame. Just something to play with. It'd be fun to download it in here. I may make some kind of example and then we install it here, because we could install Pygame on these machines since we have write access to the Python directories. But I better make sure it's not going to corrupt Python first before we do that. Alright, we're done with that chapter. We've talked about syntax, we've talked about logic. What is a logic error? Logic error is when you've made a mistake. They press the up key but your character runs to the left, right? That's our fault, the programmer's fault. They did the right thing. So that's a logic error. That's different from a runtime error or an exception. That's when it reaches a state where it blows up, right? It hits some kind of divide by zero or whatever. It wasn't caused by a failure for us to create the right logic. On the other hand, we could have prevented that bad data, right, from causing the program to crash, right? We could find out that we could not save the file or that they entered 0 or whatever and not execute that code. We could use try and except or if statements or whatever to make sure it's going to work good. So that's the syntax error. That's the logic. So you could have syntax, logic errors,
divided by 0,
and then runtime, like divide by 0 or file not found or things like that. Bad data, right? Bad data, or file not found, or could not connect to internet. Those are all examples of runtime errors.
such as y equals 1 divided by 0.
That'd blow it up unless we put it in a try except. That would work. I could go up here and put 1 divided by 0 and it would capture it, but I better put a different error message in that case. So probably it better be done in a separate try block. All right, let's go on to chapter 2. I'm not going to even assign y'all a chapter 1 exam because
It's pointless.
as long, well, not pointless. We've entered some good stuff, but I trust y'all to be able to remember what a function is and what syntax is, right? We've typed these into notes, 2 days in a row, so we're good to go.
Question.
Yes, sir.
So with our tests, I'm thinking, is some of it going to be like what is, and you fill in syntax or?
Yeah, we could go, when we do Mind Tap on Thursday, we'll go into one of the exams and you'll take a look. And my own personal exams are a combination of things like multiple choice, true, false, and fill in the blank, where fill in the blank is some kind of syntax. Like write a statement that prints a message. Well, you'd write that. You'd put print, parentheses, and whatever message. Or write a statement that'll convert input to a number, right? And I'd tell you whether I wanted a float or an int, and you'd type that in. So it's all the above.
No. Thanks.
All of the above.
All right, let's go grab the next PowerPoint.
Chapter 2.
I should make my own quiz for this stuff, for this particular chapter. All right. And fundamentals of Python, first programs like addition, software development, data types, and expressions. Well, we've been talking about data types, so we're good to go there. What's an expression? An expression is a calculation. I've got a couple of expressions in here already in my notes. If I go to my program, wrong. If I go to my program, well, that's an exception. I mean, an expression, but it's a pretty simple one. A more complicated expression would be something like this. X plus 2. And normally you assign the results to something else, right? So y equals x plus 2. Right, this is the actual expression part, but usually we just, Or something like this, if we had if x equals 4, x equals 4 is the expression.
Or,
And then x equals 2 is the expression. Notice the double equals as opposed to the single equal.
double equals mean Boolean.
Yep, this is a comparison. It's an if statement. You want to check a value, you're going to use double equals. If you're going to assign a value, you use a single equal. And why'd they do that? Well, just to tell Python that you're doing one thing or the other. So single equal is what's known as assignment. So whatever the expression is on the right hand side, it gets calculated and then assigned or stored in that variable. So that's what single equals for. Double equal is logic, right? Comparison. And Nathan said Boolean, which is right. It gives you a true or a false. That can be used inside of an if statement or a while statement. All of these purposes, are going to use double equals rather than single equals. And you'll make the mistake at first of using, single equal where you should have used double equal or whatever. And then you'll have to fix it. You'll learn pretty quickly. If you get stuck, wave your hand, I'll come back and help you, or send me a text and I'll point it out.
You'll be like, hey, it's meant to be a Boolean, not a
That's
Sunday.
right. Okay, so let's download this guy. These little preview modes that Canvas shows you here, kind of for the birds. I wouldn't do that. If you have some PowerPoint viewer installed on your machine, I would always download the PowerPoint and view it using PowerPoint. That's if you have it installed. And I need to send you all the link where we can supposedly download Office and use it as Rose students for free. Alright, so objectives. Describe the basic phases of software development. Again, this is kind of background information, and so again, we're not going to spend a lot of time talking about it. But you got to know it. And then use strings for terminal input and output of text. We've already done that. Use integers and floating points and arithmetic. Yeah, we've started doing that. Construct arithmetic expressions. That's just like saying x equals 2 times 3, y equals x plus 7, z is equal to the result of that divided by, 24, whatever. And initialize and use variables with appropriate names. So far, I've not been using appropriate names. I've been using single letters. A good variable name probably has several letters in it to make it a whole word so that you can understand the code perfectly when you're looking at it. But I've been using single letters because we haven't actually been doing, useful data processing. These have all been pure examples, right? So if this was what is your age, I should have stored it in a variable called age. Or what is your birth date, I should have stored it in a variable called birth date. Single letter variable names are really to be avoided. On the other hand, I'm going to use them everywhere, lots of places, because they're easy to type, right? And if I give you a full thing like birth date, somebody's going to type it bith date without the R, right? And then they're going to be stuck because they can't see that error, not because you're dumb, but it's really hard to spot errors in your own code sometimes, right? Just like when you're writing an English paper, the best thing to do is to give it to somebody else to proofread. Of course, nowadays everybody just runs a proofreader in Word. The same idea, right? Because it's really hard to see your own errors, or it can be. Fortunately, Python at least tells you the line number where the mistake occurred, but still, right? I don't want y'all to have to figure out that you typed in, you swapped the R and the T in birth date or whatever. So when we're doing stuff in class, I will use single letter variable names more often than I wish you would use when you're writing a program. You want your variable names to be meaningful. Meaning that if you look at it, you understand what it is, right? If I see some later program that says density equals, mass divided by volume, that's a lot better than if I go in and I see D is equal to x1 divided by x2, right? If I see D is equal to x1 divided by x2 in the code, what's D? I don't know. What's x1 and x2? I don't know. But when it said density is equal to mass over volume, you understood immediately. Now, our programs are going to be simple enough that you probably wouldn't be stuck if you did, those single letter variable names. But when you write large programs, it's going to be a lot more important. You might come back a year later and need to edit your program, and you won't be able to figure out what you did. Or if you give your program to somebody else to maintain, you can be sure that if you work in a company, a large company, part of a large programming team, then people come over here and hit you with foam rubber mallets or whatever, if you're choosing bad variable names or stuff, because it's going to make it very difficult for them to understand what your code is doing. So the development of software, planning and organizing. The Waterfall Model. The Waterfall Model is getting the customer request, or your own idea, right? Analyzing it, designing it, coding it, and then integrating it. Well, we usually skip the integrating step because we're doing it on our own machine, right? And we just press the F5 button or whatever and it runs. But if you had to give it to somebody else, you'd have to, go to that machine and install Python and put the files in the right directory or whatever so that it would run. That's the integration step. And the last one is the maintenance. Maintenance is when you're correcting errors. They figured out that if they entered A is equal, that they entered 7 as the data, then it blows up, or that it does the wrong thing. you or somebody else, a maintenance programmer, which is a common first job when you're a programmer, have to go in and fix it. And this is called the waterfall method. It's more the cascade method, but what is a cascade? A series of small waterfalls, because if you make a mistake in the implementation, you might have to go back to the design, redesign it. If there's a mistake in the design, maybe it's because they gave you the wrong specs, right? They gave you the wrong customer request, and you analyze it wrong. So you might have to go back up, right? So these can be like little loops or big loops, right? So wrong design, you got to go back to the analysis, see what was wrong with the analysis. The analysis may be because the customer, and this happens a lot if you do professional programming, the customer will list the things that they want, and you try to do a good analysis from it. You design it, you show it to them, and then they said, no, I really wanted it to do this, right? If you're lucky, you get to charge them more for that. If you're not lucky, you have to go and make the fix for free as part of the, So, like this, right? Customer request, analysis, design, and so on. Programs rarely work as hoped the first time they are run. So you have to perform extensive and careful testing. Now what we do as programmers, usually, is to write it so it'll run. What do I mean by that? I wanted to calculate the density, of O2 at a specific volume and mass and blah, blah. So I wrote the program, I entered the data correctly, and it ran. Boom. I'm done. The program runs. Programmers write program to run. But we didn't complete the job. We didn't make it handle errors. So quite often, there's a testing department working with you trying to break your code, trying to enter wrong data or prove that, it doesn't run perfectly. And then when you get those reports that it doesn't run perfectly, the programming team has to fix it. You have to do that yourself if you don't have a team, right? And you need to do it yourself anyway so that your testing team doesn't think you're an idiot, right? So you want to do as much of the testing as you can before you pass it to somebody else. So, pie chart. Designing the code takes a little bit of time. And not analyzing the code takes a little bit of time. Implementing the code supposedly takes about the same amount of time as each one of these steps. Who knows how they came up with this? I'm sure IBM did a study, or Microsoft, or somebody. Integrating the code takes a little bit of time, and then maintenance takes a huge amount of time. And you're familiar, if you're a game player, with the fact that if you download Steam, there's probably going to be a bunch of updates to your program if it was a brand new program, right? Because people will push it out the door to get some buyers, and then they have to start getting it to work, right? And so they keep publishing updates that you then have to download. That's the maintenance step. Or maybe they're adding new features. That's better, right? Actually you're getting, more for your money worth. So strings, assignment, and comments. We've talked about comments. Comments are these things, right? That's a comment. Or you put, triple quotes. And I misspelled it, right?
Multi-line.
And then, right. That's a multi-line. This is a single line comment. Right? We've been doing that since first or second day we were here, so we're good to go on the idea of comments. Text processing is by far the most common application of programming. I don't know about that. I mean, yeah, sending text messages or letting them write email or use Facebook or whatever, that all involves text processing. Computers were invented to do mathematical calculations. In the 40s, Americans invented computers to make better weapons and nuclear bombs and artillery tables and calibrate, bomb sites and stuff like that. So that's why Americans built computers while the English wrote computers to crack codes, right? The Enigma code that the Nazis used. So different purposes. That was text processing, whereas, Americans used it for math processing. But whatever. They say that it's the most common application in computing. We're not going to do much text processing. We're going to do math for the most part, but not all the time, right? Once we get through the idea of doing, math calculations and stuff like that. And by the way, if I give you a program that requires a math calculation and you can't get it right, don't sweat it. Just ask me. This isn't an algebra class, right? You're not going to get counted wrong because you can't figure out how to calculate the blah, blah, blah. So just ask me, right? Usually I'll put in my assignments, if you can't figure it out, ask me. But always, Always feel free. I can't get this density calculation to work. Well, this isn't a physics class. I don't expect you to have that memorized. And even if I gave you the formula, if it doesn't work, I'll help you with it. So a data type consists of a set of values and a set of operations that can be performed on those values. Well, what does that mean? That sounds all techie. This is a data type. And what do we know about ints? You can add them, you can subtract them, and stuff like that. And you can use them too as parts of a list or as an index into a larger group of data. Floats. Well, you can also add them and subtract them. Those are the operations that they support, but they can't be used as indexes into a larger, because if you say I'm gonna execute step 1.8, well, I want the 7.1th item, right? Well, that's not going to work, because you need the 7th item, or the 8th needs whole numbers. So the operations that are allowed on a float are a bit different than the operations that are allowed on ints. And then strings. Strings support the plus sign, so it looks like addition, but you can't multiply two strings together. I can't multiply the word Fred by the word Donald, right, and get useful results. But you can still use it. Well, it just won't even compile. It's a syntax error. So, but you can use the concept of the plus sign to do something. For strings, I'm going to end my quote, and I'm going to say first name, how about just FN, equals Bob. Last name equals Roberts. And then their name equals the first name plus the last name. Now, this isn't correct. There's a kind of a mistake in it. And if I print out the name afterwards, you'll see what the mistake is real fast. This plus sign is called concatenation. It's not addition. I'm not adding the value Bob to the mathematical value Roberts. It's doing concatenation, which just means appending, right? So now I'm going to run it. What is the value of x? Yeah, whatever. Well, I certainly did add, concatenate Bob to Roberts. It's real easy to fall into the habit of saying add rather than concatenate. I'd rather say one syllable rather than a Latin word, right? But anyways, what did we do wrong? I don't like that output. The user doesn't like that output. What would they wish that to be displayed as? Yeah, we want a space. So why don't we modify our concatenation statement, our expression, so to speak, to have a space in it? Right? Now to run well. What is x? Yeah, okay. Whenever we write a program and it requires user input, it starts getting annoying when we want to test things that are further down. But anyways, okay, that's much better. So this is an expression, right? From here to here is the expression, and this is an example of concatenation. Concatenation. Now that can be tricky in a way, because if you have this, A is equal to 1, B is equal to 2, and C equals A plus B, that's going to equal 3. No, it's not. Let's print C out. Because these are adding the strings together. It's concatenating the strings together. It's appending B to A. So what is it going to print? Is it going to print 3? No, it's going to print 12, right? Because it concatenated them. Because they're not numbers. That's why I keep saying we have to convert them to floats or ints to do math, right? So it printed 12. Created that. Not 3. Because A and B are strings.
Nice. Go to Andrew.
Don't need a PowerPoint one anymore. Get rid of it. Okay.
What?
So ints and floats are numeric data types. We've been using them. They represent numbers. What is a literal? A literal, kind of a weird concept, but it's the stuff that you literally type into the program. I'll show you some literals. That's a literal. That's a literal. Is this a literal? No, because it's calculated, right? It's calculated. That is a literal. That is a literal. It's technically known as a string literal because it's a string. We had some literals up here, right? When I said that, that's a literal. Why? Because in order to change it, I have to edit the program. This is not a literal because we typed it in right up here. We typed it in while running the program. We could type in something else. It's a variable. It's not a literal. So stuff inside quotes are literals. Numbers are literal, like that. Just a different concept. And then our numbers can be stored in variables, or maybe some kind of calculation is based on those literals. So this is a numeric literal, and that's a string literal. Does the print statement have to have a literal involved in it? No. Down here, it had a variable involved in it, right? No literals involved, no quotes or anything. No 1s, 2s, and 3s. Same for that one. It's not printing out a literal. It's printing out a variable. So, I'm going to add a comment. Literal is data that has that, or where the program has to be edited for the data to change. Variables store literals and user inputted data and calculations results. Another name for literal is magic number. Like if I have this, x equals 6.022, and I need an exponent, I wish I could do e to the 23rd like you can in chemistry and physics, but instead I have to do times 10 to the power of 23. Right. That's our good old exponent operator. Anyways, and then I say, yeah, divided or multiplied by, 78, whatever. You don't know what this is. Yeah, maybe you do if you've taken a chemistry class.
That looks like scientific notation.
Yep, scientific notation, and it's Avogadro's constant. Yeah, okay, so who cares, right? But we would definitely need to know what this was when we were scrolling through the code. It's a literal, but we stored it in a constant. What I would have done is this. If I'm going to use a constant over and over and over, I would assign it above. I would have done Avogadro's number, right? Avogadro's, right? Something to represent, right? I don't want to just say AVG. I'm going to just leave it as AV equals this. And I'm going to cut that part. Cut Control X. And I would have said AV. And I would paste that there. Why? So that I could use AV over and over and over. Right? Because I'm probably not calculating just one number of grams or whatever. I'm maybe calculating it 20, 30, 40 times in a row. So I stored it in a variable. Some languages would call this a constant. This variable a constant. Python doesn't have the idea of constants, so we pretend it supports constants by making these uppercase letters. If you see a variable that's uppercase letters, you're not supposed to change its value later on, right? What is the most famous constant? Pi, right? So if I say pi equals 3.14, and then I can use it elsewhere, right? I could use a calculation.
Or in infinity of numbers.
Yeah, the circumference is equal to 2 times pi times some kind of radius, right? See, we ought to be using variable names because I don't know what 10 means. But that's lame. It's not nearly precise enough. I'm probably going to have to go back in and edit the program and make this more precise, 3.14159. And if I'm really smart, I'll figure out how Python already has it defined, right, somewhere in it. And so we could figure out how to use Python's version of pi, which is really, really long, really, really precise. But since I stored it in a variable, then I can use it over and over and over. And if I have to change it, I only have to change it in one place. I don't have to go and search in my code and do a search and replace and find every example of where I changed it. Say for Avogadro's number, right? This is not the precise value of Avogadro's number. It's just what I happen to remember from chemistry 10 years ago. I know it's much more precise than that. And if my calculations were wrong, I would need to go and change that constant.
The first AV is capitalized and the second one isn't, so wouldn't that mean...
You're right, that's a syntax error. Boom, you got me, right? This should have been a caps. Excellent. Okay.
And the program has to be like, eh.
Yeah, the program wouldn't run. All right, so AV and PI are, pretend I put the in there, are constants, meaning they should not be changed while the program is running. The value of pi isn't supposed to change, right? It's you know, once you pick a value for pi, it's not supposed to change halfway through. You know, we're not the creators of the universe. We can't change the value of pi. But we can put in a more sophisticated version, a more precise version by editing the program. But we should not come back down here later and say pi equals 3 or AV equals, you know, the average of test scores. Because if I do that, then it's no longer Avogadro's number.
Avogadro's number?
Yeah, in this avocado number. No, that's a joke. Avogadro's number. In this language, constants are declared in caps. That's actually true for most languages, but it's really important in this one because there is no keyword that means constant. In C and C++, you don't bother typing this note unless you're going to learn those languages. You use the const keyword, right? In Java, you use the final keyword to mean the same thing. Pretend that's there like that, right? Yeah, all sorts of different words. And then the compiler catches it, right? If you try to change the value of a constant after it's declared, it's actually officially a syntax error. Well, for some reason, the guy who invented Python did not support that idea. Whatever. He's smarter than we are, so we'll just abide by, you know, his language that he invented. In Python, there is no such keyword.
Now, so if you try doing the braces in Python?
Braces, yeah, if you use these braces, no, that's not going to work. In this language, we can skip using parentheses in a lot of places that other languages require, like in if statements and while statements. We don't have to have parentheses in them, while in those languages you do. So it's just a gentleman's agreement, or gentlewoman's agreement, right? It's got quotes, or excuse me, if it's in all caps, we know that we better not reassign that variable for some other purpose halfway through the program. We're getting close to being done. We better stop here. Did I come up with any homework at this point? No, I don't think we've gone much to the point where we could do more homework. Why don't we give ourselves a break today? So let's make a Dropbox so that we can either indicate that we were here with a text note, or you can upload any notes you typed in.